All right, so our second part of fundamental theorem of calculus, they call this part 2 in our textbook, is defined the following way. If f is continuous at every point of the interval, this is a very specific interval that you'll be given, then capital F is an antiderivative of the function f on the same interval from a to b. And the integral, I'll write this bigger so you can see it, from a to b of the function is the antiderivative evaluated at b minus the antiderivative evaluated at a. So we get the antiderivative function, we plug in the two limits, a and b. It's going to have to be in the order that's given to get the correct answer, f of b minus f of a. It's called the integral evaluation theorem, is another name for it, or part 2 of the fundamental theorem of calculus. Even if you get a negative area, we talked about this, it's okay because that means you have area underneath the curve versus positive area that would be above the x-axis in a curve when you're solving it. So keep that in mind. It's never f of a minus f of b, it's always f of b minus f of a. And it seems very simple because it is. It's an idea that we've already studied in last chapter and looked at how to find antiderivatives. Now we're just going to take them one step further and evaluate them. So instead of putting on plus c in the antiderivative, that was what we call the indefinite integral. Excuse me. We're going to instead actually figure out the area. So we're going to simply plug in the two limits of integration and then solve them. Here's just a couple extra notes at the end here. Any definite integral can be calculated without taking limits, without calculating Riemann sums, and it's as well as without effort, as long as the antiderivative of f can be found. So in other words, what this is telling us is that we don't necessarily have to use rectangles. That's our Riemann sum. We don't have to use the definition of limits, which we looked at how to do that earlier. That's the same idea with the Riemann sum. It takes the idea of an infinite number and taking the limit of an infinite number of rectangles and putting them underneath a curve to get the area. This is another strategy. I want you to think back to the concept we looked at earlier. Area, integration means area, and area is a way of finding accumulation of rate of change, or accumulation of change is the way I defined it on Friday. So we now have in our basket, as I call it, of ideas of how to get area, rectangles. So we can put a bunch of rectangles on either by hand, we can put 1,000 on using our program if we know the function. We can use geometric shapes to find the area. And now we're going to use a third idea. We could use antiderivatives if I know the function and could find its antiderivative. The last thing we'll look at on Monday from after break is called trapezoidal rule, putting trapezoids inside of an enclosed object rather than just underneath a curve. We can do a little more with trapezoidal that we can't do with other things. Here are some examples. Evaluate the integral from 0 to 5 of x to the 3/2 dx. So all we're going to do with these examples is find the approximate area using antiderivative method. We need to figure out what the function was that we start with in order to get this to be the derivative. So you have to think in terms of backwards when we do antiderivatives. You have to think about the same thing we did previously in last chapter. What could be the answer to this. So we can work backwards. Remember the idea is that we bring down the power, subtract 1 from the power. We can work backwards on this to think about the answer. So I'll give you a minute to try this one. Right, what's our answer? What's our power? 5 halves, good. Add 1 to the power instead of subtracting 1. So what number do I have to put in front? Because there's no number in front here. Correct. So if you bring down the power, the 5 halves and 2/5 will cancel each other out. Subtract 1 from the power, voila, there it is. That's the antiderivative. Now we're going to evaluate that from 0 to 5. So I'm going to give you some notation first. So we're going to take 5 and plug that in, minus f of, so it's f of b minus capital F of a, plug in 0. So figure out the answer for me. We need 2/5, 5 to the 5 halves, minus 0. What do you got? 22.361. Anyone else get something different or get the same? Same? Got that? Okay. That's its area. We're done. If you graph it, look at it, you're finding the same thing as with rectangles. You're just doing it in a different way, finding the area under the curve. Oh, the other method we learned obviously is F and I and T. So one of the things you can do is compare your answers. Obviously, when we get to the end of the chapter, the test that you're going to take will be testing you on using various methods to find areas. And so that will be rectangles, F and I and T, antiderivatives, trapezoids. You'll be tested on the various methods in which to calculate and estimate area. All right, let's do the next one. Antiderivative what's my power? Let's do it in pieces. What's this part? What's the power? X cubed. Now notice I need a 3 in front. So do I need to put a number in front over here? No, because if you take its derivative, it's 3x squared. That's it. Plus, what's the antiderivative of 1? X. All right, we're done with the antiderivative work. Now let's evaluate it from -1 to 3. So first thing we do is plug in 3. 3 cubed plus 3 minus, and then plug in -1. -1 cubed plus -1. And figure out an answer. So again, I'll just write it up here. This is f of 3, f of b, minus antiderivative f of a. Doesn't matter how long the antiderivative is. You just plug in the b number, that's 3 in this case, into everything you see for x in the antiderivative, and then subtract, and then put in the other number the A, for everything in the antiderivative. It doesn't matter what it is or what kind it is of antiderivative. What are we getting for a number? What's our area? 32. 32. Yep. Yeah. Okay. That's it. That's our answer. That's our area. Questions so far? All right. Same thing there. All right. How to find total area analytically. This is what we're doing right now, basically, is finding the area analytically. And here's what we're looking at. I'll show you some examples of some problems you're going to solve for me on the board here, just to show you how this works in terms of figuring out our areas. To find the area between the graph and the x-axis over an interval from A to B. And here's what happens. Part of it's underneath, part of it's above. Maybe you have to partition it into sections because there are two functions like a piecewise that are grouped together. So we partition, if we need to, from A to B with the 0. So in other words, if you're going to go above the curve and below the curve and above the curve again, you can't just take one integral. You're going to have to do the integral of the part above, the integral of the part below, and the integral of the part above again. Does that mean it's different? No. The antiderivative is you do once. Once you figure it out, then you're going to partition it into those sections. You'll get the wrong answer if you just integrate from 0 to 10 and there's part of it above, part below, and part of it above. Then we integrate, as it says, over each subintervals and add the absolute values. Now this again, we talked about this. Absolute values, adding them is the same as saying area above minus the area below. So whether you do absolute value of each section and add all the areas together, or whether you do area above minus area below plus the area above, if there's three sections, one above, one below, one above again, it doesn't matter. You'll get the same results. This is just the calculus description of a way you can do the problem to get total area no matter what. Notice the word here, total area. They want a positive area. So what they're telling you is give me a positive area. Even if the area is below the curve at some point, make it absolute value positive, in other words, and then add all the areas together. So we're going to try a problem like this and see how we do on it. I'll just mention this again because we talked about this. This is just talking about the F and I and T idea. To find the total area, a couple people have been asking about the idea numerically on the graphing calculator. You can use absolute value to get positive area within F and I and T. I don't know that it's necessary because if you have a -3 area, you know the absolute value is 3. So I don't know that this one is really even necessary to talk about. Or you could do, minus -3s plus +3 if it has a -3 area, let's say. But I'm just throwing that out there because when I put that slide on so people can see that, you can put that in the calculator. Probably not needed. All right, so let's do a problem. First, I want you to graph it between -2 and 2. Find the area between 3x squared minus 3 and the x-axis between -2 and +2. All right, we have our picture of 3x squared minus 3. It intersects at -1 and 1, the x-axis. We need to find the area between the graph and the x-axis, so I've shaded in those three regions. I need to partition and divide up and integrate into 3 separate areas. So tell me how I would write this. From where to where? It's the same function. Again, don't forget your dx. Sometimes I forget. If I forget, you can let me know. So what are my partitions? From -2 we're starting to where? Yep. Then from -1 to 1, and then from 1 to 2. Very good. We only need to find the antiderivative once. We're just going to have to do a lot of calculating in the calculator to get the final area. So let's write out an antiderivative once, and we can just copy it twice more. Bless you. So what's my antiderivative of 3x squared? X cubed minus 3x. All right, so there's our antiderivative. Now we have to just evaluate it. I'm going to write it 3 times. We do f of b, so -1 cubed minus 3 times -1 minus f of a. So that would be -2 cubed minus 3 times -2. Get an area for that. And we do the same thing here. F of b would be plugging in 1. 1 cubed minus 3 times 1. Minus, plug in -1. -1 cubed minus 3 times -1. Get an area for that region. And then same thing here, plug in 2. 2 cubed minus 3 times 2. Minus, f of a would be f of 1, so 1 cubed minus 3 times 1. And I will give you a few minutes here to put it in your calculator and get a final area for each part, and then we'll add them all together. Right, our areas then are 4, -4, and 4. They want total area, so absolute value or minus a negative. Area above minus area below is okay, either way. Add them together. For total area, we want positive, just area. We'll talk about that in a sec. So what's our total area? What's our total area? 12, yep. All right, difference would be if they just asked for area, it would be 4. Because 4 and the -4 cancel each other out, and then another 4 would be 4. So if just area would be 4, total area is 12. Just area, you include the negative in you just add all your numbers together. In this case, we're finding total area, so you take absolute value of each one, add them together, and we're done. Post that on here.